Hi folks, my name is Kasper. I'm working at the University of Aachen, Germany, and I'm here to discuss a decoder of the Tori code, which was first introduced by Jim Harrington in his thesis. And this is a project that started off with student Dominique Michels, and I will also make connection with the Decodoku program by James Wooten. So what we see here is a Tori code. A lattice of qubits, 27 by 27. Well, you don't see all qubits. You have these light gray dotted lines, and so there are 27 horizontal and vertical lines, and the qubits are on the edges between all these crossing points. And what you do see is the qubits. Here, there's some of the qubits you do see, and those are the qubits that have an error. So we want to minimize these black dots. So you see clusters of errors. There's a cluster of error here, and here, and here, and here. And you want to minimize these clusters. Now, some clusters are problematic, others are not. This is a big cluster, which is very problematic. And the point is that it is a single string of errors starting all the way up here and ending somewhere here. These clusters are not as problematic because it's a closed loop. We don't really care about closed loops. Now, as time goes on, errors accumulate, and we want to prevent that these clusters become bigger and bigger. So that's what we see happening in this movie, right? The cluster becomes bigger and bigger, and at some point the cluster becomes too big. It becomes too big. Hence, our quantum memory is destroyed. So that's what we want to prevent. So the problem is we cannot just measure all these qubits. We cannot just measure the location of all these black dots and then just remove it. That will already destroy our quantum memory in one go. The only thing we can measure is the endpoints of these open strings. So we can measure where such a string begins and terminates. Right, so these are these red dots, and then all these red dots together form the syndrome of this error pattern. These are such a red dot is a defect or an anion, and such a closed loop doesn't have any defects because it doesn't have a beginning or endpoint. And in the hand of this syndrome information, we want to minimize the number of errors. So let's go to the beginning of when there are no errors. Let's see how the game works. So the point is due to some process, thermal environment, whatever, some errors appear. And we want to remove these errors. So due to these errors, we get, at the endpoints, we get these red dots. And a simple strategy would be just to pair up these red dots. You also see these isolated red dots. That's just because we have a measurement error. We somehow try to measure the fact that there is a red dot here. There shouldn't be a red dot, but nevertheless we conclude there's a red dot. Something's going wrong. That could also happen. So we try to pair up these guys and try to conclude that we have a measurement error here. And that's done by this decoder, and then some of them are successfully removed, some of them are left, and then new errors appear each time step. So here's a set of new errors. The old errors remain. Try to annihilate them by means of these red dots. So we move these red dots together. Some of them are successfully removed, others are not. Now, the point is that this decoder is very special in the sense that it consists of cellular-automaton. And you should imagine a little computer, a little processor located at all of these junctions, all of these crossing points of this this smallest gray grid. And these cellular-automaton can take decisions based on these red dots and based on the red dots around themselves. So for example, this little machine here, this cellular-automaton will say, hey, I have a defect, that's bad. Hey, you also have a defect. Okay, cool. Let's annihilate each other. Let's remove this error. Let's flip the qubit between us. And that's what happens. And also these defects here, they say, hey, I have a defect. Oh, and they can communicate along diagonal. So they also see here, they see each other. They say, hey, you also have a defect. Cool. Let's annihilate each other. And that's what happens. But sometimes that, let me stop this. Let me go back here. But sometimes that doesn't happen very successfully. So, for example, what happens here? This guy says, hey, I have a defect, but he doesn't see any defects around himself. So he's like, okay, what should I do? Should I move here? Should I move here? And then the computer is programmed in such a way that these defects are moved to the center of these larger squares. That's where these larger grids play a role. This defect is moved to the center of this larger square, and this is also moved to the center of this larger square. And in this case, we're in luck because that's exactly what we're supposed to do to annihilate this cluster. You see, they're both annihilated and the full cluster is removed. We're not always in such a luck. For example, here, these defects already reside or already are located in the different squares. So if this guy is moved to this center and this guy's moved to this center, they won't be annihilated with each other. They'll just move further away from each other. So then that's indeed what happens. So the thing is that we try to cluster or try to move all these defects to the center of these squares and remove these defects in a next step on a higher level. So to say that these squares are again cellular automata. They are slightly larger cellular automata. They can move this defect and annihilate it with this defect here. So let's see where that happens successfully. That doesn't happen successfully here, actually. I know how this movie proceeds. Let me go to a location where it does happen successfully, somewhere over here. So what we see now is that some errors will appear here. Yeah, that's it. Here, some errors will appear here. There's a defect here and defect here. They're moved to their respective centers. There you go. And now these, let me just stop it there where these defects will communicate with each other and they will annihilate each other. But that communication is all done in a local fashion. So this cellular automata will say, is programmed in such a way, hey, I'm the center of a cell, but I have a defect. And then it broadcasts this information to all these other centers, to this guy, this guy, this guy, this guy, and this guy. And this guy does the same thing. And it broadcasts all this information around itself to all these larger cellular automata. And at a certain point, they realize, hey, we both have defects. But this takes some time because it's all implemented locally. So it takes some time for them to realize, hey, these are defects that are just sitting here and not being removed. And then at some point they say, okay, we should annihilate with each other. So this guy is moved here. But as you say, this is done rather slowly due to the communication speed between these cellular automata. Also, once they've decided to annihilate with each other, it also takes time for these cellular automaton to communicate to the 3 qubits between them that they should actually flip. And this also takes some time, as we see in the movie here. So these will communicate to this guy, and this guy to flip, and that takes, so we can speed up the movie a bit further. That will take here, they're flipped. So you see that this local decoder has, it's very slow in removing longer error chains. And this is indeed problematic, as we see here in the beginning of the movie, where we have such an error chain from this center to this center. And it takes some time for them to communicate. But hey, before it even realized that here the errors were neighboring, this error was already due to other errors moved here. And they, let me stop it for a while, they cannot see each other. So then, because they're cellular automaton with the same rules as these small computers, they will then again decide to move this syndrome to the center of this even larger grid. So that's why we have these these thicker lines. So we see that happening. This one has moved here. This one in 2 steps went here and then went here. And then the idea is that this longer chain will be removed at this even larger scale, moving this defect from here to here. But we see that the quantum memory is actually corrupted before this even happens. So the upshot is that we have these cellular-automaton, these are local computers, that try to decode this theory code, which are actually quite stupid because they can only take their conclusions based on information they have and the information around them. They're quite stupid and they're quite slow in removing longer error chains. Now, you might wonder, why are we interested in such a local decoder? Well, for 2 reasons. One being a fundamental reason and one being a more practical reason. A fundamental reason that in physics you're always restricted to some certain speed, some communication speed. At most this is the speed of light, so it's not really a practical consideration at this point, but in some sense it always takes time for information in this part of the lattice to be communicated to this part of the lattice. So these cellular-automaton are by construction incorporate this speed of communication. The other point is that you also should consider the computational effort to remove all these syndromes. So if we go back and we look at the movie a bit further, here we have some syndromes. What's the computational effort that needed to remove all these syndromes? If you would do one big decoder, the amount of effort to be able to conclude, hey, we should remove this cluster, this cluster, this cluster, this cluster, it's quite simple. But nevertheless, if you have larger and larger lattices, if we are able to build some grid of like 1,000 by 1,000 qubits, it will take quite some time, and in this time new errors appear. Whereas the cellular-automaton, because they can only take conclusions of depending on themselves and their neighborhood, they will take this conclusion very rapidly, and hence they will be synchronous with the error pattern coming in. Okay, so this was decoding the Turing code with the Harrington decoder, and thanks for